All right, so section 4.4 is on modeling optimization. It sounds like it's a big deal, but it's really just basically using the first derivative and geometric formulas to find max and min values. So this is going to be all about story problems, okay? But your end goal in modeling optimization is to at some point you're going to find the derivative and you're going to set it equal to 0, solve for critical points, and then find the min or max depending on what they're asking you. Okay, so optimization is just finding the max or min of a function. So in this first example we're going to look at, it says what is the smallest perimeter possible for a rectangle whose area is 36 inches squared. So what this means is because it's asking for the smallest, we are minimizing. What are we minimizing? We're going to minimize the perimeter equation, and we know that perimeter is always going to be 2 times L plus 2 times W, right? And that is our end goal. That is the equation that we are going to find the derivative for and set equal to 0. But as you notice here, we have two different variables. So in optimization problems, they will always give you additional information that you can use to eventually end up with one variable. So here they tell us that the area is 36 inches squared. So here the area equation is our side equation, and we know that area is equal to length times width of a rectangle, and so they tell us what the area is, so 36 equals length times width. Okay, and now the idea is we're going to use the side equation to solve for one of these variables so that we can eventually get rid of the L or the W. So here it doesn't really matter which one you pick. I'm gonna solve for W. Let's just say W. Alright, so I'm going to divide both sides by L. So the equation that I'm going to end up with is W is 36 divided by L. Now the reason why this is important is because I am optimizing the perimeter equation, and we already said that the perimeter is 2L plus 2W. But because we have two different variables, we can't really solve this right now. We have three different variables actually. So what this does is it allows me to take this W and plug it in over here. So now my perimeter equation is 2L plus 2, and what is W? It's 36 over L. I'm going to simplify this down just a bit before I actually start solving it analytically. So this is P equals 2 times 36, or 2L, sorry, plus 72 over L. So now we want to solve the perimeter equation analytically. Alright, and remember, minimize means you want to find the local min, basically. So when you're solving analytically, what we want to do is we want to find the derivative of the perimeter equation. So if P equals 2L plus 72L to the negative 1, I'm just moving that L up, the derivative is going to be 2 plus, oh, forgot to put the negative. So this becomes a negative because the negative comes down, negative 72L to the negative 2. So now that we got the derivative, what we can do is set this equal to 0. So 0 equals 2 minus 72L to the negative 2, because remember, we want to find the min, and to find the min, we need to find the critical points. So you solve this, you subtract both sides by, or you know what, I want to get rid of the negative right away, so I'm going to add 72L to the negative 2 to this side equals 2. I'm going to divide, well, okay, you can do that, but remember that this L to the negative 2 is actually on the bottom, so 72 over L squared equals 2. So now I'm going to multiply by L squared on both sides to get that out of the denominator, so 72 equals 2L squared. Divide by 2, so 36 equals L squared. Take the square root of both sides, so L is going to be plus or minus 6. But we're not going to worry about the negative because this is about a perimeter. So are we ever going to have a negative length? No. So now I know that L is 6. And if L is 6, what's W? Remember, at one point we did solve for W. So if L is 6, then W is 36 divided by L, which is 36 divided by 6. And so W is 6. So what is the smallest perimeter of our rectangle? Is if the lengths and the widths are the same, so the perimeter is 2 times 6 plus 2 times 6, and that's going to be 12 plus 12, so it's 24 inches. So to answer our question, what is the smallest perimeter possible? 24 inches for an area whose 36. Okay? Now the procedure for solving max and min problems. Oh, and the geometric graphically, so solving it graphically, you basically get the derivative and then find the zeros. We'll talk about this a little bit in class. Okay? So the procedure for solving max and min, I'm actually going to change it up a little bit from what you guys have in your notes. That's why you see mine are gone. You always want to draw and label a picture so you have an idea of what it is that you are looking for. And then you want to write the primary equation. Okay, the max or min equation, what they are asking you to maximize or minimize. And then 3, I'm going to put a star by it, and we'll talk about that in a second, is you're going to write the secondary equation, the side equation. Okay, you're going to use this info in the primary. Then step number 4, I'm going to put another star. Step number 4, you're going to solve that secondary or the side equation for a single variable. And plug it back to the primary. Step number 5, you're going to take the first derivative and then set it equal to 0 and solve for the critical points. Step 6, you want to basically, you're going to be doing the first derivative test. Remember, that's going to be on a number line with your critical point 1 and your critical point 2, and then you're going to figure out where your max or your min is depending on what it is that they are giving you. And then number 7, you're going to answer the question. And then number 8, you're going to verify your results. Okay, so it's a little different than what you have. It's just a little bit, it made more sense to me, so hopefully it makes more sense to you, okay? All right, so let's start with our first example. So our first example says that a rectangular field is to be bounded by a fence on 3 sides, and it's rectangular on 3 sides, and it has a straight stream on the 4th side, so that means we don't need a fence there. Find the dimensions of the field with a maximum area that can be enclosed with 1,000 feet of fence. So, because we're finding the maximum area, that means we are maximizing. And what are we maximizing? We're maximizing area. And we know that area is going to be, what is the equation for area? For a rectangle, it's length times width. I just like to write that down to remind myself. Now I want to draw a picture just so I know what I'm looking for. And I have a fence that's going to be 3 sides, and it is a rectangle. And on the 4th side is going to be the stream. So that means this side is not going to be part of my fence. So really, I just need to figure out y and y. Those are going to be the same because it's a rectangle. And 1x. Okay? 1x. And I know I'm changing it from L and W to X and Y, but honestly, it depends on what you want to do. We could have left it as L and W, but I do like working with X and Y first. So our area equation here is area equals X times Y. Okay? Now, well, I kind of don't use this, but let's solve it. What was our side equation? All right. So our area equation is this. This is what we want to maximize. Now the information that they give us that's extra so that we can end up with our one variable. So our side equation, I hate the way these notes are set up, honestly. Our side equation is the perimeter. But here the perimeter is only 1x plus 2y's. And they told us that the perimeter is 1,000. Or we have 1,000 total to use. So x plus 2y is 1,000. And I can use this equation to solve for one variable. So what is my one variable equation? I'm just going to solve for x because it's easier. So x is equal to 1,000 minus 2y. So there's my variable equation used for my side equation. And I'm going to use this and plug it in to what I want to maximize. So that's going to go in for x. So now area is equal to x, which is 1,000 minus 2y times y. All right, so before I take the derivative, I want to simplify this. So this is 1,000y minus 2y squared. And now I can take the derivative. So that's 1,000 minus 4y. And now when you take the derivative, you want to find the critical point. So that means you want to set it equal to 0. So this is 0 equals 1,000 minus 4y. We're going to solve for y. So I'm going to subtract 1,000, divide by -4. I end up with y equals 250. So if y equals 250, what is x? remember, we solved for x in the one variable equation, so I'm going to plug in that 250 into this equation. So 1000 minus 2 times 250, which is 500. So x is going to be 500. All right. Now for this specific problem, they wanted to find the maximum area used. Correct? We solved for our y, and we got our y is going to be 250. So if this is 250 and then this is 250 and then this is 500, that does work because that gives us 1,000 feet of fencing. So what is our maximum area? It's going to be 250 times 500, and what does that equal? So 125 0 0 0, and that's in feet squared. Okay, and see, we didn't really need to find any interval solutions here because we only solved for one. There was only one y left over, so I didn't need to make my number line and then put down 250 here and then figure out that this is going to be positive and then this is going to be negative, because there's only one. Okay, and just by checking that this worked for the perimeter tells me that it does work for the area, and we'll talk more about this tomorrow. All right, next problem. So this problem says that an open box is to be made from 16 inches by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and folding up sides. What are the dimensions of the box of the largest volume? Okay, so what are we maximizing here? We're maximizing the volume of a box. So we're maximizing volume. And we know that the volume of a rectangular prism is length times width times height. Okay? And so our volume equation is length times width times height. Our one variable equation, aka our side equation that we're going to use. So what information did they give us that we can use? Honestly, at this point, they don't really give us any type of information. They tell us that an open box can be made from 16 inches by 30-inch piece of cardboard. So I don't see a side equation. Maybe you guys can. So if I don't see a side equation at first, what I'm going to do is I'm going to draw a picture and see what it is that they're asking me. So I'm going to draw a picture of what they're saying. And they're basically saying that we have an open box that is 16 by 30-inch piece of cardboard, and we're going to cut out squares so that we can fold up the sides. I'm sure you guys remember this picture. I even remember it from when you guys were in freshmen. We did a problem similar to this without using derivatives though. Now, I don't know how big these sides are, so I'm going to label them as x's. I don't know how big these are that I'm cutting off, so I'm going to label them as x's. And the idea is that when you cut these corners off, what you will end up with is a box with folded up sides. See, it's very important to draw a picture so you can actually analyze this and see what it is that you're looking at. So think about it like this. This long side is going to be 30, and I'm taking this part off and this part off, so it's going to be 30 minus 2x. And on this side right here, the shorter side, is going to be 16 minus 2x. So ideally, oh, and then this part right here, which is very important, how tall is this? So this part right here, it's x. So really, what do you see here? Do we have two variables? No. So once I drew my picture, I realized that I can just minimize the volume equation, which is volume is length. And what is my length here? 30 minus 2x, or sorry, 16 minus 2x, but it really doesn't matter which one you do first, second, or third. My width is 30 minus 2x, and my height is x. So that is my one variable equation. Now before I take the derivative and solve it analytically, I want to simplify this down. So we're going to FOIL first, and then I'm going to distribute the x to everything. But I'm just not going to show that in the video. You guys should know how to do this by now. So our FOILed completely problem is 4x cubed minus 92x squared plus 480x. So that is my one variable equation. Or I'm sorry, that is my equation that I'm solving, because here we did not need a side equation because we already had one variable. So I'm going to take my equation and I'm going to find the derivative. So you get 12x squared minus 184x plus 480. I'm going to set it equal to 0. And of course this is a quadratic, so how do we factor this? Step 1 in factoring is you have to pull out a GCF if you can, and in this case we can pull out a 4. And what we're left with is 3x squared minus, seconds, minus 46x plus 120. And keep in mind, you can solve this graphically right now by finding the zeros of that quadratic in the calculator. So I'm going to continue factoring. You guys can do this on your own, but I basically went through and I found two numbers that will multiply to to 360 and at the same time add to negative 46 and factored this out, and you get 3x minus 10 and x minus 12. Alright, and now to solve this we use the zero product property. Remember, you can't solve this guy because he doesn't have an x, and 4 cannot equal 0, so 3x minus 10 equals 0. X minus 12 equals 0. You solve it, you get x equals 10/3 and x equals 12. So you see here I have two critical points. Unlike the previous problem where I only had one, so I didn't have to use the derivative test. I just found that critical point and that was my answer. So having the critical points, I'm going to do an interval test. and I'm gonna, so my 10/3 is here, my 12 is here. This is why I hate the way this is set up, because it goes back and forth. And then remember, to find the max or min, I'm going to plug in some numbers on this side, so less than 10/3, so less than 3, let's say 0. If I plug in 0 into the derivative, what do I get? So this is -10 times -12 times a positive. It's a positive. If I plug in a number from this side, let's say 10, so this is 30 minus 10, which is positive, 10 minus 12, which is negative. So positive times a negative is negative. And if I plug in a number on this side, let's say 20, so 3 times 20 is 60, minus 10 is positive, 20 minus 12 is positive, so that's positive. So based on this, which one, and what are we looking for again? Are we looking for the max or the min? Remember, we're looking for the max. So where is my max? So think of this. The graph is increasing, and then it starts decreasing, and then it starts increasing. So that means my max is right there. So our max point is at x equals 10/3. And what is, so if x is 10/3, could we figure out what our max volume is? Yes. Do we need a y here? We did not need a y because our volume equation is all in x's. So you just take your 10/3 and you plug it into your length times width times height. So 16 minus 2 times 10/3 times 30 minus 2 times 10/3 times 10/3. And I'll let you guys get the maximum volume for this problem. Okay, we're getting on to 27 minutes in this video, so why don't we stop here? I do want you guys to do the homework problems that go with these first 3 examples that we did. Honestly, I don't have the book in front of me, so I can't tell you which problems they are. Just make sure that they're similar. Now, this problem's a little bit different because you're taking a rectangular sheet and you're turning it into a cylinder. So I'll make this into the part 2 video. And then the last thing that we're going to do is we're going to talk about inscribing figures, which is easier than it sounds. But I am going to skip over the last example in your notes, which was, it's about cost revenue, so economics, just because honestly we have 1 week left of instruction and we still have 3 sections, so there are going to be some things I'm going to skip over. And if you're taking Calc BC, you're going to do it in the summer for summer homework. Alright guys, enjoy, and please do the homework before you get to class. This is not an easy section because it is story problems and you guys freak out with story problems.